This is the Tutor Wizard. What we're going to do is basically I'm going to give the solution to, I posted on Facebook, problem about filling the magic square. So we're going to give the solution now. What's involved in that, or what's the problem first of all, and what's a magic square? A magic n by n square is a rectangular array of n rows and n columns. In this case 3 by 3. So this is the 3 by 3 grid. On the original phone or on the keypad, what we would have in this array, we're going to ignore the star and the 0 and the pound, but other than that, what we're going to notice is, if you stare at this a lot as a kid or an adult, I guess, but you may notice that all of the sums of every row and every column add to a number which is divisible by 3. Also the diagonals is 7 plus 3 is 10 plus 5 is 15, so you get 15 this way, and you also get 15 this way. And all of those numbers, 15 is 3 times 5, and 24 is 3 times 8, and 6 is 3 times 2, and 18 is 3 times what?
6.
Someone else had to do them. I guess I could have done them all. Did I miss one? Yeah, there's a 12 there. Now can you do it 3 times
4?
So I noticed that as a kid, that when you look at the phone, all of the sums of all of the rows and all of the columns and the diagonals all add to a number which is divisible by 3. Now what we want to do actually is play a different game from that scenario, and we're going to take the numbers from 1 to 9, and we're going to put them in here, and that's why we're going to call them A, B, C, D, E, F, G, H, I when I argue the solution. And then what we're going to do with that is we're going to try and put the numbers in there so that every row and every column and every diagonal, both diagonals, add to the same magic sum, which we're going to call M. So that's the game, and then we're going to find out what the sum is, and then we're going to show that there's only one solution up to symmetry, and we'll show you how to give that solution explicitly. This is the game we're trying to play then. What we're trying to do is, in an n by n grid or array, in this case the 3 by 3 we're going to look at, and that's what we're going to call it. We're trying to put the numbers from 1 to 9 in there. 1, 2, 8, 9. Now we're going to take those numbers one at a time. If you actually have them, you can draw little pieces of paper with the numbers on there, and it makes it a much more fun game than trying to draw it into the boxes on paper or something, because then you have to continually erase, same as Sudoku and all those kinds of things. So, or take fridge magnets and actually make actual numbers that you have, and then you can play the game, just draw a piece of paper and just draw like you would for tic-tac-toe, and then you can play along. A lot of the games that I'm going to post are going to get more and more complicated, so you can't just try and think them through. You have to actually try to build them and try and play the game. And essentially this is what math is. And that's just what I like to do. I like to take board games or two-player games and these types of things, and then start by having a game that we play and we have fun with, and then systematically analyzing it and squeezing all the fun out of it, I'm going to guess, from your point of view, I guess. Let's distill that fun out and then just rigorously have a way of always computing and then winning. A technique of a strategy. This is what I like to use math for. Basically, I have a statement. I claim theorem. The magic sum is 15 in a 3 by 3 magic square. If it's going to happen, it has to be 15. Proof. What's a proof? I need a logical deduction to the fact that that's going to actually be true. How am I going to do that? Here's where the key to ingenuity is hiding your sources, says Einstein. I'm just going to steal. If you didn't know, steal it from me now. I stole it from someone else, Martin Gardner. Wizards shouldn't tell, otherwise it doesn't look like magic. Magic squares. The magic of magic is that it's not magic. That's the magic. I'm going to call them A, B, C, D, E, F, G, H, I, because that's what we do in math there. Satan had said I had to put the letters into the math. There they are. Why? Because I don't know which ones or where they're going to go yet. So these represent, all those guys I'm going to pick them, one of them from there. If I cleverly do this, and then it's going to get a little mathy, so watch out. If I add these three things, I claim that this row has to be M. If I add those three things, and if I add these three things, it has to be M. And if I add these three things, it has to be M. So now add those 3 rows. Those 3 rows added together is 3 M's. M plus M plus M. On the other hand, though, this is A plus B plus C plus D plus E plus F plus G plus H plus I, which is all the numbers, which is 1 plus dot 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 plus 9. And Carl Friedrich Gauss at the age of 5 showed that this is 9. 9 plus 1 over 2, the sum of the first 9 integers, which is 9 times 10 over 2, which is 9 times 5, which is 45. Coincidentally, what does that tell us? That says 3m is equal to 45, or dividing m is 45 over 3, which is 15. That's correct. QED. There's the proof. I now don't have to think about or guess what the sum is going to be. If you have a solution to the 3 by 3 magic square, it has to be a 15. Next. Now what I'm going to do, remember, we've got the grid now, and now I've deduced A, B, C, D, E, F, G. What do I do with this now? Now what am I going to do? I'm in my mind, I've already spent a lot of time with this, and I stole the clever ideas from Martin Gardner. What I'm going to do is give us 3 things, which is force us to give us the solution, and up to symmetry, it's always the same solution. There's only one solution, up to where I start putting the 1, essentially. So I'm doing 3 things. The first thing I did is I know it has to be 15. I'm now going to use that information in my further arguments, and this is exactly what math does. We prove one thing, and then I'm going to use it for other things that I want to prove further on. So now I have a theorem that I stated, and I proved it. M is 15 if there's a solution to this. Next thing I'm going to do is E is 5. E is 2.7. In this case, the center is 5, i.e. the center square must be 5 for a solution to exist. We have to have 5 in the center square, is what that's going to claim. We're going to call it corollary. Corollary is something that follows directly as an immediate consequence to the theorem that we just proved. So I just proved theorem M is 15. As an immediate consequence of that, I can deduce the fact that the center gets the square. Oh, I'm old. The center square must be 5. How am I going to do that? Also, Martin Gardner, an extremely clever idea. What he's going to do is this. He wants to say, I need to compare the M to the E and get an equation somehow. Mathematically, we know. And we know that when we're talking about sums, when we start summing things, we can, and then once we have a sum, once we've done this, we can say that equals M, and then we have equations. That's where the equation's going to come from. So what Martin sees is, he's going to add certain clever columns or rows in this scenario, and then solve for E in that scenario, and it will have to be 5. E will have to be 5. So if these are the numbers, and that's where that's, here we go. Let's just do the proof. Proof. There's my shorthand of proof. Poof. Assume we have a solution that looks like this. A, B, C, D, E, F, G, H. What I'm going to do is, then I'm going to show, is where I'm going. Ask yourself what you've assumed, and ask yourself what I want. And I've assumed from the theorem, that's why it's a corollary. The pieces of information I know are, I have 15 is the sum, and I'm assuming that I have a solution that's put, the A, B, C, D, E, F, G, H, I are put in this way. Then I'm going to show that, what do I want? I want E to be 5 in this scenario. I'm going to set up equations and show that through a couple, this is implies. Indeed. I'm going to add the 2 diagonals and the Greek cross. And what does that give me? All 9 numbers, so the sum again of 45, but also because of the E's in the middle and a bunch of those extra E's, and then I can solve for E. I use my information now. What that says is, this is the sum again, which is 45. 45 is 3 times 15 plus 3e equals 4 times 15. I do it that way because now I see I'm going to move to the other side, and what's 4 something? 4 15s minus 3 15s? 1 15s. 1 15s. let's move it. Let's squeeze it in. What that says is 3e is equal to 4 15s minus 3 15s, which is 15. And oh, there it is, drum roll. That says e has to be 15 over 3, which is 5. The center square must be 5 if there is a solution. If there's a solution and m is 15, e must be 5. QED. QED is quod erat demonstrantem, what it was that I was supposed to show. Next, center gets the square. 2, we now know that theorem, m is 15, and corollary, the center square must be 5. Corollary 2. One can't be in a corner square. I don't like R's and F's. F-er. Up to symmetry, I'm just going to argue one and then say the other 3 are the same. So what do I mean? I keep saying up to the symmetry. What do we mean by that? There's 3 kinds of squares in a tic-tac-toe or in a 3x3. Corner squares, there's 4 of them. Side squares, we call them, there's 4 of them. And then center gets a square. We already know what he is if there's a solution. So now, please know that corollary 1 part 2 tells you that if you're looking for a solution, if you don't have 5 in the middle, you're not going to get it. You're not going to get 1. That's what it's telling me. 5 has to be in the middle, then go from there. And now this will just force the solution. If you now realize that 1 can't be in any of these, those are all bad. Up to symmetry, 1 has to end up going in here somewhere, in one of those. And we know 5 has to go in there. But if 1 has to go in one of these, we're going to argue, why is that important to me? Oh, then we can start just building the solution. Who has to go here now? And logic. Who has to go there?
9.
9, because the sum has to be 15. And that's what we're going to get. So this is extremely important. From these 3 things that we're going to get, and this is corollary 2, the last piece of information, if 1 can't go in the corners, we have the solution. We have all the solutions up to symmetry. There's 8 of them, but there's only 1 up to symmetry based on where I put things. I'll show you those also. We'll draw all 8. Let's do it. All right, how do we prove this? We need a few more details. I know this is a 5. I'm taking numbers from here. That means now in my argument, I've just taken 5 from there. Now what I'm going to say is, whoa log. You're like, what? I did not expect that to be the next thing you said. Whoa log. I got all of you. Without loss of generality, not generosity. We're not going to have any generosity. A bunch, maybe. Without loss of generality, that was the mixture of the 2 of them now. What we're saying is, up to symmetry, it doesn't matter where I put the 1, the argument will be the same, because the 4 corners where I place that will end up being the same argument, essentially. We can place 1 in the top left corner. Also, let me back up. I'm going to use reductio ad absurdum, or proof by contradiction. I'm going to assume we have a solution and 1 is I said F's and R's and S's, in a corner. And then I'm going to show that that can't be true. Under that assumption, I'm going to try to say that I do have a solution and I've put 1 in one of the corners. Well, I know that the sum is 15. I know that the center square has to be 5, so I've already used the 5, and now I'm taking the 1, and I'm assuming that without loss of generality, it's in the top left corner. Now, just like the disembodied voice behind the camera just pointed out, who had to go here? The 9. So who has to go here? A 9er. 9er. Did you throw a 9er in there? Yes. It's like with the 9er has. So I've picked 9 out of the set. I'm only allowed to choose 1 each. This is picking without replacement. We'll do that later too. Now what do I have to do? I have to argue that I've assumed I had a solution, but then I can't have a solution. Why? Well, This is what I'm going to focus on now. And who did I call those? Go back. I'll do it. A, B, C, D, E, F, G, H, I. So that I had those guys. And I didn't know what they were called. And so I had to put them back in there. But what does that say? That says C plus F plus 9 has to equal 15. There it is. And this column has to equal, the sum of those has to be 15. And so does this. So G plus H plus 9 has to be 15. And then what I get from that is C plus F has to equal 15 minus 9, which is 6. And G plus H has to equal 15 minus 9, which is 6. So these two spots, the two numbers I picked, those have to sum to 6 somehow, and they have to be distinct from each other. They have to be in here, and they have to add to 6. And so do these ones. And now I look in there. Who adds to 6? Okay, I got 2. I take 2 and I take 4. And so suppose I put them there without loss of generality. Again, this is why the argument becomes hard. And it's like, how do you argue this? Well, there are cases that fork a little bit, but it doesn't really matter whether I argue it here or argue it there. They'll both happen. Watch what happens. So suppose I have to I assume I'm going to get a 2 and a 4 in there, so I have 6 and then I have a 15 in there. Now what happens? There's no other numbers that I have left. I have 3 and 6 and 7 and 8 once I've used the 6 and the 4. There's no other numbers in that list that I can use for C and F, which will add up to 6. Any pair of those, I've got 4 left. How many handshakes do I have to do? 4 choose 2. But when I compare all of those things, you'll see that none of these, if I take 2 of these, any 2 of those pairs, they can't add to 6. First of all, here's an easier argument. Say I use one of them as a 3, best case scenario, then the other one has to be at least 6 anyways. How could they add to 6? Because these ones are all 6 or larger. So that can't happen. And if I don't use a 3, then I'm using just a combination of these, and they're all 6 or larger, so that sum will be larger than 6. So none of those combinations can add to 6. What does that tell me? 2 and 4 are the only numbers left that sum to 6. And this is a contradiction. Why is this a contradiction? Because I need 2 pairs. I claimed I had 2 pairs that would do it. So what's wrong with this? I assumed I had a solution where 1 was in the corner. Therefore this cannot be, and 1 can never be in a corner. Now we're going to get the solution systematically. So the home stretch, what we're now going to do is systematically give you the solution, and then we'll list all 8 solutions up to symmetry, and then I'll show you what I mean by up to symmetry. There's only one solution, but if you rotate or reflect the solution, you get another arrangement, but up to that symmetry, it's the same unique solution to this puzzle. Once it grows, holy crap, does this grow fast. For the 4x4, there's 880 unique solutions up to symmetry. There's 7,040 if you don't count symmetry. So there's only one here. Yay. Take it easy, enjoy that, because it's gonna get crazy in the next videos. What do I now need with this? I'm gonna relist these numbers. So what do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm putting them in there. Already what we found from our theorem and 2 corollaries is that the sum has to be 15 if there's a solution. If there's a solution, 1 has to be in the center, and A and C and G and I cannot be 1s. So the 1 has to be somewhere in these. Already up to symmetry, what I'm going to say is, without loss of generality, B, F, H, or D could be 1, and the argument will be the same. Why? You can already start seeing, I'm going to make 1 here because I want to make the Siamese method of filling this, so that I can show you in the next video. There's more than one technique for doing this for 3x3 and 5x5 and 7x7, and all of these. We're going to get bigger and bigger and bigger. If you look on Facebook, I posted a bunch of pictures. I have a page where I showed one for 3x3 up to 12x12. I found a solution and I took a picture of this. It does exist solutions for every array for larger than 3, and there are many, many solutions. This blows up in your face really fast. Here's the one solution for this. 1. I take 5 out, it has to go in the center. So you can algorithmically, systematically, step by step make this, and you'll find the solution, and you'll get all 8 by putting the 1 in where you put 1 first. You'll get 4 from there, and from each of those, depending on where you put the 4 and the 2, and the 2 and the 4, you'll get all 8 solutions up to symmetry. Well, what did you just say? I'll show you explicitly. Step 1, put 5 in the center. It has to go there if there's a solution. If you're looking and you haven't put 5 there, it's not going to happen. You're looking for a unicorn. Oh, unicorns don't exist. Step 2, I know 1 can't go in any of the corners. So without loss of generality, I'm going to put 1 in the top center square. Step 3, 9 has to go opposite 1 now. Now I've just used those guys. What's next? The argument that said 9 couldn't be in a corner, essentially, and so therefore 1 can't, is the fact that if 9's in a corner, I need 2 sums that add to 6. And in that argument we just found, let's use that information. What did we find? Don't forget, the only 2 that do it are 4 and 2. So that's got to be step 4. Use 4 and 2 and plug in where they go up to the symmetry here, and then that's where you're going to get the other 4 in each of the cases where we split for the first 4. I can put 2 and 4 or 4 and 2, and then that will give us the other cases. In this one I'm going to put 2 here, so I get the Siamese method. Step 4, put the 2 and the 4 in, or the 4 and the 2. You'll get 2 solutions based on that, whether you do that. So now I've used the 4 and the 2. What does that do for me? Step 5, I now have to put these in. That tells me that I get 9, so that guy has to be a 6er. And then this was 7, and that has to be 8. And then now it just fills itself in. Step 6, these have to go in now, because why? I get 12, so this has to be a 3. And I'm not even, you can turn your thinky brain off. Doop. 7's left. That's it. Now let's do the up to symmetry. Let's list all of those and show you what I meant by that. Here they go. I'm going to run that same algorithm. Step 1, if there's a solution and there's the 8 up to symmetry, 5 goes in the center of all of them. And now step 2 on the top row is where we're going to get the 4 different ones. Up to symmetry, it didn't matter where I put 1. In the one I just did, I did it there. But it could go here, or it could go here, or it could go here. It has to go in a side one though, not a corner. What does that do for me? And then you'll see where we're going to get that. We're going to have a 1, or a 1, or a 1, and a 1. Step 2 is the 9s, or 3, the 9s have to go in. Opposite the 1. Rogue 9. Rogue 9! Don't go rogue. What's the next step? 4. The 2 and the 4 have to go opposite to make a 6 for the 9. In this case, I did 2, 4. So the other one I'm going to get is do this, 2, 4. And those ones, that's where I get 2 more from, is what I was saying. And then in here, I'm going to do 2 and 4. And then I would get 4 and 2. And then here I'm going to get, where's the 9? Here's the 4 and 2, and then so that I would get 4 and 2. And then here I'm going to, where's the 9? I'm going to get 4 and 2, and 2 and 4. Then what did that do? The diagonals. The diagonals are next. What has to happen? I get 9, so that says 6 has to go here, and I get 7, and I have to get 8. And then that says what? Those are going to have to switch. I'm trying to use my not thinky brain for the second row and the thinky brain for the top row is what I'm trying to do. Be as lazy as I can. Now what does that do? I get 7, so I get 8, and I get 9, so I get 6, and then that says this has to be an 8 and a 6. I flip them. Then here I'm going to get 7. Well, that was 7. I added 7 and said it. I get 8 and I get 6. And then I flipped them. I get 6 and I get 8. And then here I get 9, I get 6, and I get 8. So here, oh, I flipped it. Thank you, row. 8 and 6. And now what has to happen in these ones? I'm going to have to get a 3 and a 7, a 7 and a 3. Here you can see where they're going to go. I'm going to have to get a 3 and a 7, so a 3 and a 7. Here I'm going to have to get a 7 and a 3. So a 3, no, a 7 and a 3. And then in the last one, I have to get, where is it? 3, 7, and 3, 7. There. That is up to symmetry. There's only one. And I'm going to give you, next time, what we're going to do is I'll show you how to find at least one solution, even though there's a huge number of them for every n. We are going to show you the Siamese method. It's called, it came from Siam originally, in the first written records of this, a clever method on how to fill all odd order magic squares up to symmetry using the Siamese method. What that is, I'll give you a sneak peek to that. How I'm filling that is like this. I won't show you the clever technique I'm doing, but here it is what I'm using. I'm using the Siamese method of filling this, not the method I just used. What I just did was just raw logically deduce using 3 results that I proved ahead of time. I just rigorously said this is the only solution you can get in up to symmetry. There they are. Now I'm going to use the Siamese method, and for larger ones there's much more solutions. So then this is one of the techniques for 5x5 and 7x7 and all of these other ones. Here it is. 1, 2, 3, 4, 5 has to go in the middle. 6, 7, 8, 9. And notice that here n is 3. N squared is 3 squared, which is 9. N squared plus 1 is 10. N squared plus 1 over 2 is 10 over 2. The center square is always n squared plus 1 over 2 for every odd-sized order. The middle square is, you take the number 3, you square it, you add 1, divide by 2, arithmetic. You get what the value of the middle square will be. And also, you can start arguing in the next time. I can't shut up about them. N squared will always be opposite 1 in the algorithm. Please subscribe right here by hitting the button. You can see me on Facebook at Adrian the Tutor. You can see us on Twitter at Tutor_Inc. I'll see you next time. Math is awesome. So take some take some fridge magnets. Fridge magnets together seems hard.